This video is for Chapter 2, Section 3, Analyzing Graphs of Functions. Alright, if everybody would get to page 187 in their textbooks, we'll get started here. The graph of a function is a collection of all ordered pairs such that x is in the domain and y is in the range resulting from f of x. So we've been talking about that a little bit with working with our functions in the last section. Remember that f of x is kind of a substitution or another way of representing y. So the range is the set of y values. We've talked about that in the past. So therefore the range would come from our f of x's. When we plug x in, we solve our function, we get our range. Okay, we get those answers or those y's. So again, to sum that up, the domain comes from the x values, the range comes from the y or f of x values. Take a look with me at the bottom of page 187. Checkpoint number 1 down there. We're going to find the domain of f. Okay, well if we are looking at the domain of f, what x values are represented by that upside down parabola? Okay, well if you look furthest point that's graphed or marked to the left has a -3 open dot value, and the furthest to the right has a closed 3. So the domain, or the set of x values, we're going to use that soft parenthesis for the -3, because that open dot tells us that it does not include -3. And then the closed dot indicates that it does include the +3, so we use that hard bracket. Letter B says find the function values of f of 0 and f of 3. So if we are looking at the graph there again, the function value or the y value when x is 0, take a look at the picture there, it goes up to y is equal to 3. Okay, so f of 0 is 3. F of 3, kind of talked about that a little bit already. Over there at 3, for an x value, we end up with a -6 for a f of x or a y value. Now look for the range of f. The range of our function, again, is going to be the range of our y values. Okay, so you're looking for your highest y value, you're looking for your lowest y value. Our y's go from -6 up to 3. And there we go. Vertical line test we talked about a little bit with our previous section as well. I was not about to try to recreate these graphs, so I do need everybody to turn to page 188 so that you are looking at these pictures with me. Under example number 2, that sideways curve, it definitely does not pass the vertical line test. You can see that it hits it once at the top and once at the bottom of the curve. So picture A under example 2 is not a function. Picture B, kind of a wavy, curvy, kind of roller coaster looking one. That one is going to be a function because, again, if you imagine any vertical line being placed through that graph, it's only going to hit it in one place. Letter C, even though this graph seems to be interrupted, you still have it passing that vertical line test. Okay? You just don't have a few values of x included in this graph. That's all right. The graphs that you do have, or the x values that are graphed, still result in only one y value each, so it still is going to end up being a function. So now let's look together at the checkpoint one at the bottom of the page. It's the shape of a parabola, and again, if you put any vertical line through that parabola, it's only going to intersect the curve in one spot. So that bottom one at the bottom of page 188 is also a function. Zeros of a function. We have been working with finding zeros of equations or zeros of functions. So if you take a look at example A, there's some done for you again in the book, A, B, and C. I'm going to focus on the checkpoint ones at the bottom because they are not already solved out for us. So for A, f of x is equal to 2x squared plus 13x minus 24. Here again we have one of those trinomials. I would suggest that whenever you see one of these things and you're asked to find zeros or solve, see if you can factor it. Okay, and this one does. If we place 2x and x in the first positions of our factors and look for combinations of 24 that are going to give us that 13 in the middle, you'll find that a -3 and a +8 will give us a 16x and a -3x. That's going to result in that 13x we're looking for. So our solutions for this, 2x minus 3 will end up being 2x is equal to 3 or x is equal to 3/2. There's one of our zeros. And then the second factor most of you are getting pretty quick at coming up with, the -8 that would make that factor equal to 0. Okay, letter B has another function for us. G of t is equal to the square root of t minus 25. What is going to end up making that one a 0? We would need a 25 underneath there. Okay, if we put 25 in that spot and subtracted 25 from it, we would end up with a 0. Okay, letter C, h of x. Now with functions, in trying to find the zeros of a function or the x-intercepts of a function, we are looking only for the things that will turn into 0. We are not concerned with things that make it undefined. So don't concern yourself with the denominator here. That's going to make it undefined. Focus on the top. Figure out the zeros for the top, because a 0 as a numerator of a fraction does make the value equal to a 0 overall. So x squared minus 2 equals 0 is what we want. Move the 2 to the other side. And to solve for x, we need to take the square root of both sides. So x is going to be plus or minus the square root of 2. Okay, so that one would have 2 zeros. Positive root 2 and negative root 2. Increasing and decreasing functions. A function is increasing if the value from x to x, okay, so x1 to x2 goes up, and so does the value of y1 to y2. Okay, so if you've got a point x1, y1, and you have another point x2, y2, and x to x goes up and y to y goes up, those values are going to make a line or a graph between them rise. That will be an increasing part of a function. A function is going to decrease if, as your x values from point to point go up, the y values from point to point are going to go down. A function is constant if the x value goes up and the y value stays the same. Okay, so it would end up graphing like a flat line for all of or part of a function. So turn with me now to page 190. Again, they have a few of them there where you're describing function behavior for increasing, decreasing, or constant. We're going to again take a look at the one at the bottom. It says graph the function f of x equals x cubed plus 3x squared minus 1. You're going to need to do that on a graphing calculator. I don't have one that I can put up on the slideshow here. If I do, I don't know how. So I'm just going to sort of put a sketch of what I found when I graphed this one out by hand. All right, so if this was my axis, this is kind of what mine looked like. I found a few points just by plugging in and evaluating. 0, -1 was a point. 1, 3 was a point. I ended up with 219, so it really shot up here. I had -1, +1. I had found -2, +3. And I also found -3, -1. So it kind of did the up or downy curvy thing. Okay, so I think if you put this into a graphing calculator, and again, I don't have one here, so hopefully that's sort of what it would look like. But if we're looking for increases and decreases, you can kind of see them here. From -infinity to 2 to -2. See this spot right here? Okay, on my graph, that chunk was going up. So from negative infinity to the point of negative 2 for the x values. Okay, so we're looking at domain. This was an increasing function. Now at negative 2, it started to drop. So from negative 2 until it got to x was equal to 0, it was decreasing. And then it started to climb again. So from 0 to infinity, it went up. Okay, so there's the behavior for that particular function. Minimums and maximums. If we were looking, let's back up a second. If we were looking back at this one, you'll notice that there are some points along it where we had a maximum value for a while. In other words, there were places to the left of it and to the right of it that went lower. So that would make this a maximum. Down here, this point had spots to the left of it and to the right of it that were higher than it. So this was an example of a minimum. Okay? So maybe now this will make a little bit more sense to read through. If the f of x value, remember that's interchangeable with y, if the f of x value of x is lower than the f of x values on either side of it, the point is a minimum. If the y or f of x value of x is higher than the f of x's to either side of it, the point is a maximum. If not given a picture of the graph, you're going to need to graph the function on a graphing calculator and use the zoom and trace features to find your minimums and maximums. That's something we could probably go over together as a group if you do not know how to punch that in and use those zoom and trace functions. So bring that up in class tomorrow and we can discuss that one as a group. All right, another thing that we're going to be taking a look at with these functions are average rates of change. Now look closely at the average rate of change. I'm now on page 192, by the way. We have f of x sub 2 minus f of x sub 1 all over x sub 1 minus x sub 2. Okay, doesn't that look an awful lot like a slope formula? Remember that f of x is the same as y. Remember our slope formula was y minus y over x minus x? That's exactly what we're looking at here. Other than the fact, hold on, that I messed up my typing just a little bit. Let me fix this. This is supposed to be a 2 here, and this is supposed to be a 1 here. Sorry about that. But now it's right. Okay, so remember that f of x is just another way to represent y. So we are looking at using slope to figure out rates of changes. On page 192, we're going to take a look at one of these functions together. There's one in the book done. We again are going to look at the checkpoint together. It says find the average rates of change of f of x equals x squared plus 2 from x values of negative 3 to negative 2. So here's what I did first. If I have x sub 1, I need its partner so that I have a point. Okay? So if x sub 1 is negative 3, I'm going to put f of negative 3 through my function and see what I get. Okay, so negative 3 squared plus 2 times negative 3, 9 minus 6, I get 3. So one ordered pair is negative 3, 3. That's the pair of, or the point that I get when I use x sub 1. Let's do the same thing with x sub 2. Let's find f of negative 2. Let's find the y that goes along with an x value of negative 2. So now we're going to have negative 2 squared plus 2 times negative 2. And that ends up being 4 minus 4, or 0. So when negative 2 is our x value, y is 0. Now we can implement that rate of change formula. F of x sub 2 minus f of x sub 1 all over x sub 2 minus x1. Okay, so y minus y over x minus x. So negative 3 over negative 2 plus 3, which is 1. So I get a rate of change of negative 3. Okay, let's do it again. At the bottom here, we get a new set of x values, x sub 1, negative 2, and x sub 2 is 0. So again, we need our entire point. So let's do f of negative 2. Okay, so x squared is going to be negative 2 squared plus 2 times negative 2. Okay, essentially we just did this one, right? So we're going to get 0 again. Now I need f of 0. My second x value over there was 0. So I'm going to get 0 squared plus 2 times 0. F of 0 results in 0. So here's my 2 points. When I have negative 2, my y value is 0. And when I plugged in 0, I got a y value of 0. So taking a look at that one, if we plug these into our rate of change formula, we're going to have 0 minus 0 all over 0 minus a minus 2. It's supposed to be 0. So 0 over 2 gives us a rate of change of 0. And you can kind of see that. Both of those points had a y value of 0 on it, so they didn't go up. We had a slope of 0. Average speeds. Okay, now I'm at checkpoint problem number 7 on page 192. There's 2 of these here. I decided to do B just because I felt with the function that they give us here, it was a little bit harder maybe than section A because we do have that 3/2 power on t in our function. It says the average speed is represented by s of t is equal to 20t to the 3/2 power. Find the average speed of a car from t sub 1 being 1 second to t sub 2 being 4 seconds. Okay, so if the car is traveling 1 second, what's its speed going to be if it traveled for 4 seconds? What's its speed going to be? And we're going to find its average speed then from these 2. So again, t sub 1 is 1. Let's find our function with a value of 1. Okay, 1 to the 3/2 power is just going to be 1. Okay, so this point, or ordered pair, would be 1 comma 20. So at 1 second, we had a function value of 20. Let's do then s sub 4. Let's put in 4 seconds. Not s sub 4, s of 4. Now we have 20 times 4 to the 3/2 power. All right, now quick review of 3/2 power. That's the same as the square root of 4 to the 3rd, correct? Okay, the 2 is your index, the 3 then is the power. Now 4 to the 3rd is 64. Square root of 64, 8. So we end up, when we evaluate this, we're going to have 20 times 8, or 160. So my other point at t sub 2 is 4, 160. So let's fill that into our rate of change formula now. I have 160 minus 20 all over 4 minus 1. So 140 over 3 is my rate of change, which is 46 2/3. And that would be feet per second, by the way. I didn't have a label on them. Okay. Last thing. Even functions versus odd functions. This goes back to our symmetry that we were talking about in our last chapter. Even functions are the ones that are symmetric with respect to the y-axis. We had a test to see if something was symmetrical to the y-axis, and it was substituting in negative x and seeing if we end up with the same function that we started with. Okay, hopefully that rings a bell. Odd functions are symmetric with respect to the origin. Now remember, that symmetry meant that if you subbed in negative x and negative y to your function, it returned to what it originally looked like. Okay, so we're using that symmetry from chapter 1 again. Let's play around with this a little bit. There are 3 checkpoint problems on page 193 that deal with this. I'm going to do all 3 of them with you. So it says f of x is equal to 5 minus 3x. So there's our function. All right, so if we're going to check this for even, all right, that means we are going to do our y-axis symmetry test. So in other words, we're looking for f of negative x. So plug in negative x where you see positive x in the function. We're going to get 5 plus 3x. That is not what we started with, so this is not even. It is not symmetrical with respect to the y-axis. Okay, now let's check it with respect to the origin. So now we want negative y and negative x being placed in. Now remember, this thing right over here is y, correct? So if we're going to put in negative y, we're looking at negative f of x. Okay? And we need to put in our negative x. So negative f of x equals 5 plus 3x. If, okay, so play around with this one a little bit. I'm going to factor out a negative 1. And then, if I were to cancel that so I can go back to a positive f of x, okay, so that was the reason behind factoring a negative 1 out, so I could cancel it on this left-hand side. Oops. I'm going to end up with negative 5 minus 3x. Okay, is that what f of x started out as? No. So we are not odd either. There was no symmetry about the origin. This is not an odd function. So it was not even, it was not odd. There's no symmetry here at all. Let's try another one. If g of x is equal to x to the 4th minus x squared minus 1, let's run the evens test on it first. Okay, evens test, we're going to put in negative x and check it. And if we simplify this, we are going to come back to the same function that we started with, g of x. Okay, so this one is even. It will be symmetrical about the y-axis. Okay, now if it's symmetrical about the y-axis, it can't be symmetrical about the origin, so we're not even going to run that test on it. The third one, h of x is equal to 2x cubed plus 3x. So let's try the evens test. So for y symmetry again, we're going to put in negative x in place of positive and see what we get. That is not what we started with, so we are not looking at even. How about origin? Okay, so now we want them both to be negative. So negative h of x, okay, remember that's negative y, is equal to, put the negative x's over here. So negative h of x equals negative 2x cubed minus 3x. Again, I'm going to see if I can get this negative off this side so it returns to the beginning. So I'm going to pull a negative 1 from here. so that I can now cancel or divide by negative 1 on both sides. And sure enough, it returns to looking like it did at the beginning. So this one is symmetrical about the origin. It is odd. Odd function. All right, folks. Page 194 is where your assignment starts. Please work hard on this section. We've been kind of familiar with most of the things in section 1 and 2 so far. Section 3, I think, is a whole different ballgame. So work these problems. Do a lot of the early ones. Do not forget about the application ones. You will want a graphing calculator for some of this work. So if you do not have one at home, let's focus on those in class where we can borrow one. All right? So I will see you tomorrow.